Welcome to Target IAS. I am Prakash Rajput. Now let us see our next topic, that is equipotential surfaces. So what are these equipotential surfaces? In electric field there are many points at which the electric potential is same, because electric potential depends on the distance from the charge distribution from which we are measuring the electric potential. That's why at many positions the electric potential is same. Suppose you imagine a charge here, then across it and around it, if you imagine this sphere about this point charge, the distance is from this point charge to this surface is r. Here also this distance is r, and here also this distance is r, and as you know that v is equals to q by 4 pi epsilon naught r, then this value on which v is varying only, because as q is constant and 4 pi epsilon naught is also constant, only thing which remaining is the distance from the charge distribution to the point of potential. So if we make this r constant, then at this surface the value of v at any point, the value of v at any point will be equal. So these surfaces are known as equipotential surface. If we define as an equipotential surface, it is an imaginary surface. It is an imaginary surface in electric field of given charge distribution, you can say, of given charge distribution in which all points on surface are at same electric potential, same electric potential. So this will be the definition for equipotential surface, that it is an imaginary surface in electric field of given charge distribution in which all points on the surface are at same potential, same electric potential. So उस surface के ऊपर सभी points पर इलेक्ट्रिक पोटेंशियल की जो वैल्यू होगी वो सेम होगी. So suppose you imagine this surface as equipotential surface having electric potential Va with respect to 0, suppose. So and here is one charge placed, suppose this is as location A. Now I am moving this charge from this point to A point to, suppose, B point. I'm moving this charge from A point to B point. So what you know that is, so I'm moving this charge from A to B point. So what you know that work done is uh, work done will be for moving this charge from A point to B point. It will be Q times VB minus VA if I'm moving this charge from A point to B point. Right, it will be the work done. Now since it is an equipotential surface, here the potential at every point will be same, so VB will be equals to VA. Now you see that this term will be 0. So if you are moving a charge on an equipotential surface from some location to the other, then work done is always 0 for moving a charge on the equipotential surface. Now we will see what will be the equipotential surface for a point charge. If I take this point charge, I have just now told you that what will be the equipotential surface. So as due to point charge, what is the electric potential? It is q by 4 pi epsilon naught r. So only thing remaining is r. So equipotential surface around this point charge will be somewhat like this. This is one equipotential surface. I can change the value of r and I can find another equipotential surface. I can make another equipotential surface like this. So like this there will be many number of equipotential surface if I change the value of r again. So it is somewhat like here the value is r1. So this is first equipotential surface. Here the value is r2. Here the value is r3. This is third equipotential surface. So you can see that around a point charge the equipotential surface you can say are concentric spheres. Concentric spheres. So concentric sphere. And if you find electric field at the first, like here on this on this equipotential surface, it will be in this direction. So here what is the angle between the equipotential surface and the direction of electric field? It is 90 degree. Here also you can see on any of these surfaces at every point the direction of electric field will be 90 degree. So you can say that electric field and equipotential surface are या फिर आप ये भी लिख सकते हो E and equipotential surface meet at 90 degree. So you can see that E is always normal to the equipotential surface. You can make equipotential surface for any charge distribution. Suppose I take a line charge. If I take a line charge suppose, and I want to make equipotential surface around this line charge. So for this line charge the equipotential surface will be something like a cylinder. Something like a cylinder. Because due to line charge the electric field will be like this. So at this you can see it is making 90-degree angle, and at every point on this surface the E value will be what? You know that rho L by 2 pi epsilon rho, or 2 pi epsilon naught rho aero cap. So this is the equipotential surface for a line charge such that, and you can make equipotential surface for surface charge also. So the equipotential surface is nothing but the at which the electric potential is same for every point on that surface. So if the electric field is uniform, if the electric field is uniform like this, so the equipotential surface will be parallel to each other. If you make equipotential surface they will be parallel to each other if the electric field is somewhat uniform. This is electric field and they are my equipotential surface, they will be parallel to each other. Now if the electric field is non-uniform, going like this, then these equipotential surface won't be of the same shape. They will be changing their shape according to the electric field line changing. So you can always remember that the equipotential surface and the electric field will meet at 90 degree only. This condition can't be uh, violated anywhere. So this was about the electric equipotential surface. Hope you understood. Now we'll see another thing about the relationship between electric potential and electric you already know about this. uh, like we can calculate v by minus integral of E dot dl, right? Now if you finding a small potential dv, then it will be like minus E dot dl, right? If I write this in vector form, minus E dot dl. Now you can also say that for a small change in voltage, it will be minus E dot delta L. So here it is a dot product, and I can write this in the magnitude form also. If I write delta V is equals to minus E delta L cos theta, minus E delta L cos theta. This delta L, if I take this in denominator, divided by delta L equals to minus E cos theta. Now if I apply to find the electric potential at certain point, if I apply limits on both the side, limit delta L tends to 0. So here delta V by delta L will be minus E cos theta, right? We can uh, write this as, after applying limits, dV by dl will be equals to minus E cos theta. Now here you can see that E is some constant, because electric field is like I'm finding electric due to this change, due to some electric field at point P. At point P, the electric field is constant. Suppose this is my point P at which I am finding this dV by dl. Now if you find dV by dl maximum value, if you want to find dV by dl maximum value, then when it will be maximum, dV by dl, when it will be maximum, it will be maximum when dV by dl maximum when cos theta equals to minus 1. That is, you can say that theta is equals to theta is equals to 180 degree. So what it becomes, if I put cos theta equals to minus 1, it will become dV by dl equals to E. Now you see that maximum rate of change of potential with respect to distance, what it is giving? It is giving electric field. What it is giving? Electric field. Maximum rate of change of electric potential with respect to length, it's giving the electric field magnitude. And this dV by dl is nothing but, we can, the maximum rate of change of some field is known as gradient, potential gradient. If you remember the definition of gradient, that what gradient tells, it is the maximum rate of change. So this will give the magnitude of electric field. Now you see that maximum dV by dl maximum will be achieved if the increasing potential is in the opposite direction. And what you mean by opposite direction? In the opposite direction of E. In the opposite direction of E if you go, then it will be possible to have dV by dl maximum, because I have taken this as minus 180 degree. So here if you write the value of E for, so it can be written as in the form of vector. If I want to write, it can be written as minus dV by dl, because it will be maximum when we are moving in opposite direction. So minus dV by dl max, okay, because that will give the magnitude of the electric field. And for the vector, there will be a unit vector to that equipotential surface, which is normal to that equipotential surface. So here this value will give the electric field and with the direction. If I write this thing in more mathematical form with the use of differential operator, this can be written as minus del V, minus del V. This will be the value for electric field, and this will be the relation for E and V relating E and V. So you can directly apply this formula for finding the electric field with the help of potential. So E is equals to minus del V. That is, it is gradient of the potential. So as we have found out that electric field is nothing but the potential gradient. So you can directly apply this equation as what it is giving. It is giving maximum rate of change of potential, maximum rate of change of potential with respect to distance. Okay. Now here you can see one question. An electric potential is given by this expression, and find V and E at this point. So V can be easily found out because expression is given. You just have to put these values. So here these values are r, theta, phi in the cylindrical coordinate system. So the value of r is 3 and theta is 60 degree, so it will become sine 60 degree divided by 3 square. And if you solve this, this will come as into 5.773. It will come as 5.773 volts because this value is given in volts. Now if you if you want to find out electric field, what you have to do, I just now have told you that E is nothing but minus del V, that is gradient of this potential. So this is in cylindrical coordinate system, so I have to apply the formula of gradient in the in the spherical coordinate system. So I have to apply the formula of gradient in the spherical coordinate system. So minus is already there, del V. What was the formula for the gradient in spherical coordinate system? It is del V by del R plus 1 by R del theta, del V by del theta, 1 by R sine theta, del V by del phi. And here I have to forget that here unit vectors are also there. They are a theta and a phi. A theta and a phi. So this will be the formula for the gradient. So let's apply this on. So I have to find E. It is minus already there. So del V by del rho. So I have to differentiate this with respect to R. So if you differentiate with respect to R, what it will become? Like del V by del rho. Let's find out first these del V by del R. Del V by del R. So it is del by del R of 60 sine theta by R square. So 60 sine theta will come out, and minus 60 sine theta differentiation will be R cube and multiplied with 2. So it becomes 120. This will be the value for the R component here. Now let's find out del V by del theta. So it will be 60 sine theta, 60 by R square will come out, and with respect to theta it will be 60 cos theta divided by R square, and there is no phi component, so del V by del phi becomes 0. So now put this in the formula. What it will become? E equals to, minus is already there, del V by del R. It is minus 120 sine theta. Theta is given as 60 divided by R cube. R cube is given 3. So this is the component for AR cap. If I write this, plus theta component is 60 cos theta by R square, and I have to divide by R. So 60 cos theta is 60 degree divided by R square, and there is one more R, so it is again become 3 cube, and it is a theta cap. Now I have to simplify this. So this comes as minus, this value will come as -3.85 AR cap, and this value comes as 1.11 A theta cap, and here this is minus sign already there, so the E value comes as 3.85 AR cap, minus minus becomes plus, and here minus 1.11 A theta cap. This will be the value of electric field, and what will be the unit? Volt per meter. So in this way you can find out if there is expression for V given and you have to find E, you have to first find the gradient, and then here because of this minus sign, the minus will be multiplied and you can find the electric field. Now let us see our next topic, energy density in electrostatic field. Now as you know that for moving a charge, suppose from infinity in an electric field, suppose from infinity I'm moving a charge in the electric field, so I have to do some work for moving a charge. Suppose here is in this region some electric field lines are present and I am moving a charge from infinity in this field, so I have to apply some work, I have to do some work for in moving this charge. So and if so who will do the work? The external source will do the work to move this charge from infinity to certain point in this electric field. Now if I remove this external source, what happen is this charge will move along the electric field. This charge will move the electric field. So you can see that to hold the charge in place, I have to do some work. I have to externally add some source, and that source will move the charge in the electric field, that is it do some work, and that charge will be held some position, will acquire some energy, the it will have some energy stored in it. ये कुछ ऐसा ही है जैसे कि आप वाटर लेवल पर जो जैसे बकेट भरी हुई रखी हुई है कोई, मान लीजिए it is at ground level, a bucket is filled with water, and now I have lifted this bucket and put it here above the ground level, so it will acquire some potential energy, it will acquire some potential energy. That's how if we move a charge from infinity to a certain in a certain electric field and place it some at some position, so it will acquire some potential energy, that is it will have some energy stored in it. So now let us consider there is no electric field in this space, there is no electric field in this space, and now I am moving a charge, now I am moving a charge at this location, at this location from infinity, as there is no electric field right now. So for the first charge, suppose this is charge q1, I have moved from infinity, so for the first charge there will be no work done because there is no electric field. So no electric field here, no work done will be there. Now if I move another charge, this was also placed from on infinity, I am moving another charge. Now due to this charge, it will have some electric field in this region, it will have some electric field in this region, so I have to do some work, and that work will be given as q2 into v21. If you remember, it is nothing but v2 minus v1, because it will have some potential due to the charge q1. Now if I move another charge, if I move another charge, suppose q3, this was also moved from infinity, so I have to do work done. Again for q3 it will be like v3 1 plus v3 2, that is potential at point 3 due to first charge and potential at point 3 due to second charge, right? So like this, if you take n number of charges, so you have to do some work, you have to do some work, and that work is given by, if you do for n number of charges, that total work, because here if I find the total work, I have to add these two. I have to add these two and then find the total work. So the total work expression for n number of charges will come as qi vi, where I equals to 1 से लेकर के n. So there is no need of derivation for this. You can actually understand, if I add these two, what will come? It will be 2, twice of the work done. So not twice of the work done actually. So here you can take it as the work done W1 and here W2. So the total work done will be Q2 V21 plus Q3 V31 plus Q3 V32, right? This will be the value of total work done. Now if you see that, if I do the reverse order, like if I place first Q3, then Q2, then Q1, then what will be, there will be no work done for Q3, and for Q2 the work done will be V23, V23, and W2, that is, if I move the charge 1, so the work done will be Q1 and it will be V12 plus Q1 V13. So here the work done will be Q2 V23 plus Q1 V12 plus Q1 V13. Now here and here this work done will be same, because three charges are placed, right? Same three charges are placed. So if I add these two equation, so it will become twice of W, that is work done. So if you add, so here you can collect some terms like with Q2, here what is this? Q2, it will be V21 plus V23, right? Plus with Q3, here V31 plus V32 plus what is remaining? Q1, V12 plus V13. Now here you see that V21, V23, what is this? This is basically potential. V21 plus V23 is potential at point 2, suppose, where the Q2 is placed. Potential at point 2 uh, due to charge at 1 and 3 similarly. So I can write this as V2 only, because it is the effective potential or the absolute potential at point 2. So here this V31 and V32, what it will become? V31 plus V32, what it will become? It will become V3. And this V12 and V13, V12 and V12 plus V13, what it will become? It will become V1. So that's why here this Vi is nothing but the potential at the point ith location where Qi is placed due to all other charges that are placed around. Okay, so that's why this Q2 V2, this 2W will become Q2 V2 plus Q3 V3 plus Q1 V1. So you can see that what is this? Half of, I can write it as Q1 V1 plus Q2 V2 plus Q3 V3. So that's what the expression says, which I have told that you just need to memorize it and you just have to follow this equation. Here work done will be half of the summation of Qi Vi. Understood? So now we will write expressions for energy stored in in terms of E and D. As you have written right now that energy stored is half of Qi Vi summation basically. So if I write this in better form, half summation I equals to 1 to n Qi Vi. Right. Now this is for point charges. If the point charge instead of point charge, it will be of some kind of like line charge, surface charge. So the same expression can be modified as if for a line charge it will be rho l dl rho l dl with v, right? And if for a point charge, if for a surface charge, I have to write that it will be rho s ds into v, right? And for a volume charge, what it will be? Half of integral rho v dv into the potential, right? So we can find any for any type of charge distribution using these formulas. So now if you see this expression for volume charge, here this is rho v dv, and if you remember the first equation of Maxwell, that was del dot d is equals to rho v. So I can replace this rho v from here by this, so it will become w, that is energy stored, half of integration del dot d with volume integral multiplied with potential. And if these expressions are like integrated and simplified using the vector properties of the divergence, the final expression, you just have to remember the final expression, that will be half of integration epsilon naught e square dv. This will be the first expression of energy stored, energy stored. And from here, if I want to find the energy density is nothing but energy stored per unit volume. Energy density, uh, that is energy density, if I found that energy stored per unit volume will be half of epsilon naught e square, right? If we directly write the volume after integrating the by the total volume, so this will be energy stored per unit volume will be the energy density. So as you know that epsilon naught E is D, so this expression can be written like this also. Epsilon naught E, so it becomes D dot E, or if I just take the magnitude only, so it will be dE, right? dV. So from this expression also energy density can be written. Energy density, what it can be? W T upon volume will be half times dE, half time D into E, right? Again, if I use expression and I want to write the energy density in only D form, so what I can do? Replace this E electric field by D by epsilon naught. So it will be 1 by D square by epsilon naught. So all these expressions are used for energy density. All these expressions are used for energy density in electrostatic field, half epsilon naught E square or half D times E, or half D square by epsilon naught. Here also this equation can be modified as d square by epsilon. So as you know that d and e are in the same direction, that's why the dot product is simply changing. Here the dot product was there, like d dot e was actually there, but since d and e are in the same direction, it can be directly replaced by their magnitude, and just remaining thing is d multiplied with magnitude of d multiplied with e, just that. So this is the energy stored. This is how you can find the energy stored if there is E given, or if there is D and E both are given. You can find in any way. the energy stored in the electrostatic field by this expression. Or if you want to find out the energy density, then you can use this expression. So this is about the energy stored or energy density in electrostatic field. Now let us see one question here. What it says is W1 is the electrostatic energy stored in system of three charges in a line with zero point 0.5 separation between them, 0.5 meter separation between them. If W2 is the energy stored with 1 meter separation between the charges, then which one of the following is correct? So we have to find the correct option from the given option. So here there are three charges which are placed on a line, suppose. So we can take their charges in the equal form. Their separation is 0.5, 0.5 here. Now the energy stored is given by, we know that, what is this? Half of summation of Q1 and the Qi Ji, Qi Vi. So it can be half of Q1 V1 plus Q2 V2 plus Q3 V3. So it will be 1 by 2 Q1, Q2, Q3 I am taking equal. So I can take Q outside. So it can be, I can write it as Q by 2, and V1 will be the potential due to the at the position 1, 2, 3. So V1 will be the potential due to this point charge and this point charge, second and third point charge. So it will be, what is the formula? Q by 4 pi epsilon naught R. For this distance is 0.5, and for the third position is distance is 0.5 plus 0.5, that is 1, right? Now similarly Q2 and V2 for potential due to the first charge and third charge. So it can be written as 4 by epsilon 0.5, because distance from both the charges is 0.5 for V2. So it will be 0.5 plus Q by 4 pi epsilon for the for V3. V3 the distance is first, for the second charge is 0.5 plus Q by 4 pi epsilon, here it will be 1. So after solving this, it comes as Q square by 2, comes out to be Q square by 2, and it will be 1 by 4 pi epsilon is everywhere, epsilon not, epsilon I have taken, and after solving the distances it will come as 10. So this is W1. Now the separation of 0.5 is increased to 1 meter. Now the separation between them is 1 meter. So if we solve in the similar manner which I have done earlier, we would find that Q square by 4 pi epsilon, Q square by 4 pi epsilon, and here 2 is also I can write because I have written here also. It will come as 5. So you can observe that the W1 is twice of W2. W1 is twice of W2. You can understand this thing in different form also, as you know that W is what, if I write here with different pen, what is this energy stored? It is proportional to Q and V, and as the charge is constant I can make it proportional to Q by 4 pi epsilon R, and also I can relate this as directly with R. So you can also think of W1 by W2 divided by R2 by R1. So as R2 is changed to 1 and R1 was 0.5, so you can again find directly that W1 is equals to twice of W2, which I have found earlier. So here from the given option, which option will be correct? C option, that is W1 is equals to W2 will be correct option. So that will be all for today. We will meet in the next lecture. Thank you.